question that is thrown, which is this interesting. Because look at what's happening here. Not only am I throwing a stone, one stone now, but we're throwing two stones. One from the top, one from the bottom. The top one is dropped, the bottom one is thrown up, and they both are colliding in mid-air. And they're asked to find where they will collide. So it's like one of those old times, right, where you throw... It's a kind of a variation of a problem where, the Pandavas and the Kauravas are on two sides, and then this person will throw an astra, and the other person will throw one of these missiles, and they both will collide in mid-air. And you can kind of predict where they will collide. Yeah, if done this that way, that's kind of what we're doing here. One of them is not throwing because he can just drop it. It's lazy. The other one is throwing it up. And the question is, where will they meet? Now we put a little take g equals 10 because we just solved the problem and realized that this question requires g to be taken as 10. And I think it's useful to mention. That's why just mentioning it here. Even though it's not mentioned explicitly in the textbook. So you get the answer and you take g as 10. So you look at this. Let's represent this now. A ball here is dropped. A ball here is thrown. This one with an upward velocity of 25 meters a second. This one with a velocity initially of 0 meters per second. Now, there is an approach to take here, okay? What you can do is calculate the displacement of this. So they both, let's say, are going to meet somewhere over here. Could be anywhere. Let's say it's going to be somewhere over here. Yeah. Let's say this is where they're going to meet. Yeah. Now the interesting thing then is that when they meet, they both are at the same point. Why is that interesting? Because if at that point, this body's displacement will be, say, S. This body's displacement will be the total height minus S. And the total height's been given to us. Right? 100 meter high building. So this is S. Then this will be 100 minus S. So you get where this will go, right? The really keen ones in math will know what you can do here. Write an equation for this displacement, write an equation for this displacement, yeah, and add them to get 100. Or directly take one of them as 100 and the other is 100 minus S. Yeah. Now we can do this and show you how this can be done, but we are allowing this to be done by you. We're going to take a more elegant approach. And the elegant approach requires us to spend a little bit of time on understanding what the word relative means. Yeah. So we're going to spend a couple of minutes doing this. We're not going to go too deep into it. So if you are going in a car at 50 kilometers per hour and somebody else is going along with you at 50 kilometers per hour, then when you look at them, what do you see? They're coming along with you. So you measure the speed you measure will be 0. So relative to you, the velocity that they have will be 0. Somebody else on the ground will say, no, both of you are going at 50. But as far as you two are concerned, the velocity is 0. Let me extend this argument. You are going at speed of 50 kilometers per hour with an acceleration of some 10 meters per second square. So along with the velocity, you also have an acceleration. So does this person. He also has an acceleration. Now you look at the both of you are speeding on the road. Not only are you having a velocity, you also have an acceleration. When you look at the two of you, you will see, that's right, both of you are at rest. In other words, if two of you jump off a cliff, right? Two of your friends, two and you and a friend decide to jump off just for the fun of it, yeah? Yeah, this is the part where we say don't try this at home, yeah? Jump off. Or jump off together. So both of you are going to be falling down. And as you're falling down, let's say we take them out in this building and put them here so they can talk to each other. You both can keep talking to each other as if it's a normal day. Yeah? The buildings might be rushing past. The ground is rushing at ever faster speeds towards you. But the two of you can be like, hey, what are you doing? Just talking. Yeah? And falling together. In other words, as far as the two of you are concerned, you're at rest. Bringing us to the concept of relative acceleration as well. So relative to you, that person is not accelerating. Relative to you, that person is not even moving. So taking that concept in our mind, although we've done a very quick introduction to it, we believe that most of you will be able to understand. What we are claiming is that this ball, once it's been dropped, and this ball, once it's been thrown, both of them have an acceleration of 9.8 or 10 based on this question downwards. So forgetting the number, we'll take g downwards. If both of us have an acceleration of g downwards, with respect to each other, what is the acceleration? 0. I look at him and say he has 0 acceleration. He'll look at me and say I have 0 acceleration because both of us have the same acceleration. It's very similar to this analogy. If both of us have a velocity of 50, then with respect to each other, we'll say he's 0, I'm 0. Anybody else might say something else. So if I stand outside and watch, I'll say this is acceleration, that is acceleration now. But as far as the two of them go, they have zero relative acceleration. Now, why is this beautiful? It's beautiful because once you take it this way, what can you do? You can forget G. G doesn't exist. Both of them are not accelerating. So what does this boil down to? This might be a leap of faith for you right now, but stick with us. This body has a velocity of 0 meter per second. So in one sense, what you're going to do now is go sit on one of them, become an ant and sit on one of them, and then solve the problem, right? So if you sit on one of them and solve the problem, what do you see? What you will see is simply this. This body is 0 velocity, 0 meter per second to start with. And in this frame, or in this point of view, there is no acceleration. So a body with no acceleration will retain its velocity, right? Whatever velocity it had, it will retain. 0 it had, it will retain 0. This body, the one that was thrown, has a velocity of 25 meter per second. And that will also retain its velocity because in that point of view, there is no acceleration, right? Yeah, no acceleration, 25. And that will also retain its velocity because in that point of view, there is no acceleration, right? Yeah, no acceleration, 25. What distance? So this is 25 upwards. So now the problem becomes something extremely simple. This body has to go and hit that body. Distance between them, 100 meters. Yeah, one of them is at rest. So look at how this question has become that much more simplified. This entire question now is simply a body at rest is going to get hit by another body going with a constant speed of 20 meter per second, 25 meter per second. When will it hit? It's a 7th standard or 6th standard question, right? The distance covered should be 100. The velocity is 25. How long will it take? Very simple answer is going to be 4 seconds. Yeah? Do you notice that we have cut down our complexity hugely by choosing a point of view very cleverly? By choosing this point of view, the point of view of one of those balls, we have taken and made this problem that much more simple. So this distance is 100, the velocity is 25 because the other one's not moving. How long will it take? 4 seconds. You can take the other approach and verify that both of these are going to take the same time. Both these are going to give you the same answer. Right? So when will they meet? They'll meet after 4 seconds. Here's the interesting approach today. An approach called relative acceleration. Now what we have not calculated and what we cannot calculate with this approach is where they will meet. Yeah, that we can't do with this. So what do we do for that? Something very simple, right? Because the question where assumes that you're looking from somebody else's point of view. Only there we can say where. So to do that, what we will do is, we'll take, now that we know the time though, the question becomes that much more simpler. So we'll take the top body because it starts at 0. It's easier for us. So let's take the question now. We know the 4 seconds. We know they're going to collide after 4 seconds. So if I drop the body from here, it's going to fall for 4 seconds and then it's going to collide here. So my job is just to find out what this distance is. In 4 seconds, how much does it travel? So what's my U? 0. What's my A? Yeah. To be precise, it's minus 10 meter per second squared. We've taken our up as positive. Your S is what we need. Your T is what we have. 4 seconds. So what is your S going to be? S equals UT plus half AT squared. Let's put it out here. So your S is going to be UT plus half AT squared. Therefore, it's going to be 0 because U 0 plus half into minus 10 into T squared. In this case, T squared is 16. So you get minus 80 meters. Now clearly what does a minus 80 tell you? Downwards, right? So from here, from this point that you took as your origin, 80 meters downwards is where this collision will happen. So in other words, 20 meters from below and 80 meters from the top. And that can be your answer. So when they will collide, 4 seconds later. Where they will collide, 80 meters below. We've done this using an interesting approach called relative acceleration. Feel free to watch this over and over again till you get this concept completely and grasp it totally. Because these are a stretch for us. These are all concepts that are going to be a stretch for our current level of understanding. And that is why we are going there. Right? Because it's a stretch to what we think and know right now. It's going to be a huge amount of flexibility to problem solving. So take this question, do it again yourself to understand what the beauty of this question really is.